Hello, everybody. I'm here today to talk more about physical properties of solutions. This will be basically an empirical or experimentally based talk because a lot of these effects will really require us understanding free energy, entropy, and equilibrium in more detail to put any kind of theory behind it. So we'll focus on more casual, I don't say casual, but more important experimental empirical observations at this point. Let's first talk. We're going to focus on water, although this discussion is applicable to other solvent systems as well. So let's talk about dissolving solids in water. So this could be something like sodium chloride, for example. And what we'll see is that we'll just call solubility S. This will be how much of the substance is dissolved in the liquid water. This could be in concentration units, for example, of molarity. And let's have temperature down here, whether this be Celsius or Kelvin, really doesn't matter. It's a scaling effect. We're just not going to put any numbers to this at this point. What we'll see is that in almost all cases, the solubility of a solid increases with temperature. So for example, this could be NaCl. Now, I would clearly need to have axis labeled to really put marks on here that are meaningful, but this is a general trend, and that's all we're going to focus on now. We will put numbers to these type of things later in the course for this. So for solids, and you probably know this just intuitively, that generally you can dissolve more of a substance in a liquid, water of emphasis, when you have a higher temperature. There are some exceptions. We will talk about them in a briefly later on in the course, but overwhelmingly most solids such as NaCl, KCl, etc., as well as molecular compounds as well, dissolve better at a higher temperature. Now, with gases, it's the opposite. With gases, going into solution, what you'll see is that the solubility of the gas, and again, this could be in units of molarity, and we'll have temperature here, and it's increasing as you move to the right. With gases, almost exclusively, it decreases. And so you'll have, at a higher temperature, a low molarity of a gas like CO2 or O2 in the water than you do at a lower temperature. So it decreases with increasing temperature. So this could be something like carbon dioxide or oxygen and so forth. Almost exclusively, the concentration decreases with increasing temperature. What we will do calculations for today is another effect that relates to this. Let's focus on gases for now, because we're going to come back to solids in a little bit later in the course. Let's focus on the solubility of gases in water as a function of partial pressure of the gas. Now again, what partial pressure is recall from last semester, let's say we have air over water, right? So we have a lot of nitrogen in the air. Let's focus on the two main components, and a lesser amount of oxygen. And so here's water. Let me draw my little wave here. Here's water. The total pressure in the troposphere, roughly where we're at ground level, is about 1 atmosphere. And there's about 3 parts of nitrogen to oxygen. Roughly, the partial pressure of nitrogen will be about 0.75-ish, and the partial pressure of oxygen will be about 0.25 atmospheres, roughly. And so this is a function of partial pressure of the gas, not the total pressure. So what we're saying here is, I'll just call it solubility of the gas of interest. I'll call it S. Some books will call it a C. That's fine. You can denote it any way you care to, as long as you understand what we're speaking about, and that's proportional to the partial pressure of the gas in question. When you have a relationship, it's not an equation. You can, like this, with a proportionality, you can usually write a mathematical equation with an equality if you have the right proportionality constant. So what we have here is called Henry's law. Henry's law. And what it does, it relates to solubility of gas. Now, this could have units, for example, of molarity, a certain molar concentration. And this could, for example, we might talk about the partial pressure of the gas. If you like, for example, in atmospheres, it doesn't have to be. It could be millimeters of mercury, or it could be pascals, or what have you, torr. It could be other units. But whatever it is, for this system, we will have to have a Henry's law constant that will have units of molar per atmospheres to make the units match. This will cancel this, and you'll end up with molarity on this side. You have molarity over here. And again, you scale something over here will have to be adjusted if the units don't match. You might have to convert pressure. Let's say you start at millimeter mercury or pascals to atmospheres if you have a table with this in terms of molarity per atmosphere. So that's always pay attention to the units. That's always a big thing. I'll put an asterisk here because this is where people tend to have problems. So let's work an example of a relevant equation using Henry's law. So what we still see here is that as the partial pressure goes up, the solubility of the gas goes up, and then these are tabulated roughly. I put a little squiggle here because I'm not sure. It might be page 9 or 10. If you go to page 10 in the note sets, I have a table of Henry's law constants, and they're tabulated as a function of temperature. These are given at 25 degrees Celsius. If I worked in a different temperature regime, I would certainly give you the value of the Henry's law constant there. There's nothing there you need to memorize. I would always provide that on an exam. You don't have to come in with it yourself. That's something that I would provide in the table or stated within the problem. So let's work an example. Let's say we have an industry, in industry, let's say we're concerned about carbonation of a beverage. So we're putting CO2 in water, right? That's commonly done to make soda and other carbonated beverages. So typically in industry, what they'll do is they'll expose water, or it might be sugar water. I'm not sure what stage of the process they do this, but they expose the water to a partial pressure of about 2 atmospheres. I'll just use 2 atmospheres as my choice of what the particular business is using. And so I have to look up Henry's law constant for CO2. You go to the table, and what I find here, and confirm this for yourself, is that KH is equal to 0.035 molar divided by atmosphere. So we set the equation up. Let's say we want to know what the solubility is in terms of molarity of CO2. So we just plug it on in here, 0.035. And then we have 2 atmospheres of pressure here. We don't have to convert any units. And so this ends up with being 0.070 molar because the atmospheres cancel. So that would be representative molar concentration of carbon dioxide in your beverage that you're drinking if it was prepared with under 2 atmospheres of partial pressure. The conversely, and I had to look up the exact value, and it will vary. Typical atmosphere, assuming it's roughly 25 degrees Celsius outside on a nice day, 4.3 times 10 to the minus 4 atmospheres is the partial pressure of CO2. Again, this will be a function of how much pollution, where you're at in the troposphere, and so forth in the atmosphere. Just focusing on the lower atmosphere where we're at, called the troposphere. And so what you'll see here is the solubility of CO2 under those conditions is and I got for that 1.5 times 10 to the minus 5 molar. Make that a little nicer. So it's about 4,500 times greater. You can actually figure it out yourself. Just take the ratio. You have it's greater when you're under 2 atmospheres of pressure. So, the carbonation, you're going to see over 4,000 times more. It's around 4,600 times more carbon dioxide in water than you would under normal atmospheric conditions. There is some carbon dioxide if you have a glass exposed of water exposed to the atmosphere. A small amount of carbon dioxide will dissolve into it, but nothing like when you have carbonation, and that's why the soda goes flat. When you expose it to the atmosphere, two things are occurring. One is that it has a lower partial pressure of CO2 over to how it was prepared and sealed. And then secondly, it might be warmer. You're sitting outside and so forth, and compared to your refrigerator. So that will exacerbate the effect as well. The temperature will decrease, the solubility also. So it's, be familiar with doing these type of calculations. Why is this relevant? We're talking about sodas here. Well, that's great. This will come into play when you study your biology or physiology, particularly when you're dealing with oxygenation or deoxygenation of blood, also carbon dioxide transport. That's a more nuanced situation because you have, for example, with oxygen, you have particular carriers that are responsible for binding CO2, and they have a little different, it's not as simple as just water, but the idea of Henry's law and Henry's law constant will come into play in those calculations as part of a more foundational part of it. And then the higher biological parts of it, the oxygen transport by particular globulins like hemoglobin or myoglobin in human beings, and there's similar ones in animals, will be another level upon that. But certainly the higher concentration of oxygen, partial pressure of oxygen in the alveoli of the lungs will come into play in your calculations and understanding of human and other animal physiology. So, and then obviously in environmental sciences, the effects of temperature and pressure on the amount of gases in water is important for understanding, the biology and the life that goes on in natural waters and so forth. So this is all relevant to real life processes. It's not just chem lab type stuff. So on that note, we'll continue on these lectures. I'll try to make a couple more videos today if time permitting. And have a great day. I'll probably see you again. Take care.